Well, hello. It's nice to see you folks here tonight. I'm Jeff Curtis, and I'm here as one of the folks from the San Francisco Theosophical Lodge, and I'll be having a talk with you this evening about, well, I think my stated title
It's not as good of a background, but it's
is,
a little bit more comfortable. Yeah.
okay, do I have two windows going here?
I get distracted. I get a little tired, but
I have two windows. Well, okay, let's see if this is the.
You're on.
Okay, thank you.
Oh, I
Sorry,
see. Well,
some
you can-
technical problems there. Hopefully you can all see this, and it's coming through for you. If not, I will hope you get a message to that effect sometime soon. So what I'm going to be talking with you about tonight is going to be a few thoughts on time, space, the universe, and everything. It's been an interesting day in time and space here in the Sierra foothills. We almost ended up not having this little soiree because we have some fire activity in the area, but that seems to be tamped down to the point now where we're going to be able to go ahead. What I want to do is really begin sharing with you some ideas about modern thinking on time and space, because it's obviously a vast topic and a complex one, and one that would require many such lectures in order to try and take care of. I'm going to trace a little bit of thinking in general, some history, and then weave in some of my own thoughts on how we're going to go about approaching this topic. And sort of like my series of discussions on consciousness, this will be one of what will be a series of presentations of thinking and what exists in the literature for me to draw upon. So it seems simple, right? You can until you go deep or do some deep reading, you can think, well, time and space, what's so hard about that? It seems sort of obvious. We all have an intuitive understanding of what that implies, of what that is. I am now communicating with Richard at the lodge to make sure that this feed is coming through okay. I've had some internet outages and I can't quite tell the status. If you go deeper, you start reading modern physics, you begin to realize that much of the last 120 years of development of modern science has involved very specifically rearrangements in long-standing viewpoints about space and time, what it is, and how we as conscious beings are instantiated in it. Now, we get an early and overly simplistic, intuitive sense of time and space because we grow up as children in the world. It seems like things travel in a straight line, and objects have permanence, and space extends in all directions linearly, and time flows, and it's all kind of easy if you just take it on the basis of personal experience growing up. Then in our education, lots of times we first start learning about things like Euclidean geometry. Euclidean geometry is the geometry of a flat space where parallel lines never meet, and it goes forever, and it's flat. It's a relatively simple, predictable, extrapolatable medium or container for the universe. A little bit later, we tend to start working at junior high, typically, and we begin to learn about Newtonian physics. Now, Newtonian physics, that's the physics of Sir Isaac Newton, great genius and revolutionary of his time. The physics he developed, however, grew out of that kind of intuitive container-like concept of space, and then a continuous flowing time. Those were presumed givens or foundational aspects of the reality, which he then went on to derive the laws of motion and a great many breakthrough aspects of physics at the time, but which now are under very radical revision since the early 1900s onward. And that's what I want to start talking about in segments of this series of expositions. I would point out, however, that 19th century Europeans and Americans weren't the first people to begin asking about the ultimate nature of space and time, and to begin suspecting that there was something deeper going on. There's a history of that in Eastern spiritual traditions. Maybe I'll try to learn enough about that to talk about it sometime in the future. One that I wanted to mention here tonight is in the ancient Greek tradition. There is a very beautiful, interesting, and kind of surprising, deep and insightful set of questionings of the nature of physical reality in terms of the intuitive structure of space and time that comes from simply growing up as a macroscopic creature on Earth. And this is the work of Parmenides and his student Zeno. So you might have heard of something called Zeno's paradox. Actually, it would be more proper to refer to Zeno's paradoxes. Zeno's paradox is very interesting. He used pure thought, which ends up being a remarkably powerful thing in the hands of a sufficiently smart person who just is good at doing thought experiments and looking for what's consistent, what's inconsistent. So Zeno, following the teaching and urgings of his teacher Parmenides, he came up with the following notion, which negates the entire idea of motion through space if you follow it out to its logical conclusion. So the first and kind of the parent and the simplest of Zeno's paradoxes is one called the paradox of dichotomies. And the simple statement of it would be, suppose you're in the middle of a room and you want to go over to the door. Well, okay, so you get that idea in your head, you turn your face to the door, you start walking, and a couple seconds later you're out the door, and a tenth of a second after that you're out the door. Okay. What Zeno points out and made a study of is the fact that, okay, that sounds fine, but consider this. In order to get to the door, you first had to go halfway to the door. And there's a place in space that we could call halfway to the door. And then you keep walking, and then you go halfway the rest of the remaining distance. And then you go halfway the rest of that remaining distance. And what this implies is that over the course of walking to the door, an infinite number of times you passed through the point which was halfway to your goal. And unless there's a problem someplace there in that description, what you just did was an infinite number of operations in a finite amount of time. How can you have an infinite number of operations in a finite amount of time? Well, that's kind of a problem. Well, I realize now, as a kid, I was taught Zeno's paradox, and it wasn't called that, and it was couched a little differently, but I do remember, I think in about 5th grade, some math teacher getting to the point of the idea of a paradox and the idea of infinite series, and his way of couching it was, well, suppose you got a bug that's a certain distance from the wall, and the way it works is the bug is designed so we can only jump halfway of the distance to the wall, no matter how far away he is. So First he jumps halfway to the wall, then he jumps half of that, then half of that, half of that. Unfortunately, you stop to think that through, it means the bug never gets to the wall. And this is also one of the other ideas of Zeno's paradoxes was the Achilles and the tortoise. So that one you may have heard is couched a little differently, but it's of the same kind. You'll see the pattern here. The idea there was Achilles and a tortoise are going to have a race. Achilles spots the tortoise 100 yards to distant mountain or whatever it is they're going to race to. Fire, gun goes off. Well, not a gun, but somebody shouts go, and Achilles starts running. Pretty soon he gets to where the tortoise was starting from, the starting line he was at. And by the time he gets there, maybe the tortoise has only gone a couple yards. Now he keeps running. He can run fast. Pretty soon he'll be where the tortoise just was, but the tortoise has run a little farther. That, if you think about, if you write it down mathematically and you think about how that one works, again contains an infinite number of these nested loops of getting halfway to where you want to be. In this case, Achilles catching up with the tortoise. And so you can, by strict rules of logic, conclude that Achilles never does catch up with the tortoise, which is obviously ridiculous. And so where's the problem there? Parmenides and Zeno would argue that the problem has to do with our concept of space and time and our concept of motion. And from this, they arrive at a conclusion that motion is impossible as simplistically defined, and our experience of space and time has a problem. There's something we're not describing consistently. And then ensued 2 millennia of argumentation and people trying to come up with refutations of the paradoxes or explanations and reifications of the paradoxes, back and forth, back and forth. Well, interesting. Just my point being, it's a complicated topic, and greater minds than mine have been puzzled about it for a long time. So let's get to the early 20th century, where I'm claiming things begin to change in a radical way. I wanted to mention one other thing. Newtonian physics. Newtonian physics, which is the idea of a continuous space and time, is incredibly powerful. I'm not trying to dump on that at all. What we can get out of Newtonian physics is the idea of bouncing billiard balls. And how do things work if we now get reductionistic and we think about reality as describable objects, let's say billiard balls, or extrapolate down and make those into atoms, hitting each other and bouncing off. From that simple physics, you can recover almost all of thermodynamics, the science of the flow of heat between bodies. You can put a man on the moon with Newtonian physics. You can describe something called the kinetic molecular theory of gases, which in my teaching days I taught the kinetic molecular theory of gases at a few different levels. We teach that in freshman year general chemistry courses, then we teach it at a more refined level in the junior year in a course called physical chemistry. And you can explain so much of observed reality with essentially Newtonian physics and the kinetic molecular theory of gases. So it's not unpowerful stuff by any means, but it can only be pushed so far. And the limits of how far it could be pushed began to present themselves in 2 ways in the early part of the 1900s. The first way was brought about in part by the work of Albert Einstein interpreting a range of experimental observations that had been made and published and were bothering people as of the early 1900s, actually the late 1800s, beginning most particularly with the work of Max Planck. And Einstein interpreted, he collated, brought together and interpreted a set of experimental information on something called the photoelectric effect. And his interpretations were so insightful that it allowed him to infer the existence of quanta of light, the things we now call photons. The idea that light does not come simply as a continuous electromagnetic field of some kind, but rather, even though it follows the physics of an electromagnetic field, it also is provably arriving in packets, or what we call quanta. And this gave rise to the entire science we call quantum mechanics. Quantum mechanics was forced on us by experimental reality, in other words, facts. The facts, as best we could measure them with the technology that was emerging in the very late 1800s and then early 1900s, forced us to take a step back and think, whoa, it seems that reality is not continuous. It comes in discrete chunks. Seems that reality has an inarguably probabilistic basis. There are limits to our precision with which we can know things. This has to do with the complementarity of observables and something called the Heisenberg uncertainty principle. So there was a great revolution and refinement in our thinking that was forced upon us when our technology arrived at a certain point of finesse, that we began to be able to resolve lumps under the carpet of things we thought we understood. Then, parallel to that, and also sparked by Einstein, this time in the other way, in the method of Parmenides and Zeno, Einstein, merely through power of intellect, having a heck of a mind and the ability to do crucially insightful, called Gedanken experiments, or thought experiments, he was able to figure out first the theory of special relativity, and then that was in around 1905-ish, and then about 9 or 10 years later, his theory of general relativity. General relativity is where he brought gravity and gravity fields and the fabric of space-time into his thinking. And so our ideas about space-time got their first big rearrangement with Einstein and general relativity and what it implied and what it meant. Now, the implications of general relativity were upsetting. There was known to be riots at places where he spoke because there were people who didn't want their sense of space and time messed with. That came from God, and they're God's favorite people. And anybody messes with what God told me, you're going to have all that, just like we have now. It happened then, and it wasn't until the 1920s, with certain astronomical observations performed, I believe, by Arthur Eddington, having to do with looking at the positions of stars during solar eclipses, we were able to finally nail down technologically, experimentally, that yes, it looks like relativity is a fact. It's not just a suggestion, it's not just an idea, it's not just some weird paradox, maybe we can argue it away, it's a fact. And that really has been an interesting ride since that happened. Now, let me mention a couple of things about general relativity. It would take me a long time. I don't really even understand it well enough to give a proper lecture on it. I can give you a little bit of what I know and what can be said about it. But one of the key underpinnings of the theory of relativity has something to do with what we might call now. And what is the nature of now? People think they know. I mean, come on, now. I know what that is as it's happening. We go through life pretty in touch with what now means. It's not a big mystery, right? Well, it turns out it actually is, because if you take from relativity the implications, the foundations of it, one of them is called the relativity of simultaneity. And what it means is there's no such thing as a universal simultaneity. Simultaneity is a relative concept. And simultaneity is observer dependent. In this case, observer, you could substitute in the word coordinate system. It's coordinate system dependent, or referring really to the coordinate system which a given observer of events sits at. It's not quite the same fraught and mystical use of the word observer that we might use if I was talking about quantum mechanics. So that's a subtlety there. What it means is that if you let go of the notion of now, or at least a universal now that applies over multiple and all-inclusive possible reference frames and observers, you're forced mathematically, or so it was thought for a long time, to accept a picture of the universe known as the block universe. And if you've done any reading in modern physics, or even in the more kind of popular press and philosophical books, you probably run across the term block universe. What block universe refers to is the fact that if you take the universe from point of the Big Bang to wherever it is we're going, and you strip out of it the concept of an identifiable now, you're left with the idea that what exists has always existed and will always exist. It's a continuum of what was and is still there, what is now at your particular moment of being, perception, and puzzlement, and what will be in the future, and already is, according to Einstein's model of the block universe nature of space-time. Now, a lot of people didn't like that. And that would include me and probably most chemists. You know, chemists are very into mixing things and watching reactions happen. And one of the laws of thermodynamics, which we're particularly in touch with, is the one called the second law of thermodynamics, which has to do with dispersal. So one way to paraphrase the second law of thermodynamics and the notion of dispersal would be that energy and matter confined or concentrated in one region, left to its own devices, will always find a way to disperse and occupy a bigger volume, would go to a more disordered state spontaneously. There's different ways to state the second law, and including and preferably mathematical ones having to do with the heat change associated with a process divided by the temperature at which the process occurs. But anyway, chemists are way into it. We mix things. We watch the second law of thermodynamics dictate what happens all the time. And the second law of thermodynamics is particularly interesting in this context because it's one of the only places in physics where you can find the suggestion of an arrow of time. How do we differentiate the past from the future? That's not to be found in quantum mechanics. Quantum mechanics does not provide that, at least not at first pass. This is starting to change, but not at first pass. Time is a smooth and continuous variable, and there's no real surprises about time coming from quantum mechanics. And it doesn't provide an explanation for the arrow of time. But the second law of thermodynamics kind of does. And that's important. There's another reason why people don't like and have kind of recoiled at the block universe idea, and that would be a philosophical one. And you can find philosophers of mind who started trying to get out from under the block universe idea pretty much as soon as it was arrived at. And that would be the question of free will. Because if the universe is just this big block of events that happened, and it's frozen back there at the beginning and it's frozen out there at the end, even though we don't know what the end is, because we're stuck here in the middle at what we perceive of as our now, yeah, nobody wants their free will gone, right? That's kind of a bummer. And so it tends to bring up natural hackles and a certain sense of looking for a chink in the armor of that. Well, I'm happy to report to you that the chinks have arrived. They're starting to show up now. And that's what I've been reading about off and on for the last couple days in between checking my computer to see where the fires were. Um, I, I'm almost arriving at the end of my exposition here, so I'm just going to sketch out a couple little hints about where we're going, and you'll kind of get a sense. Um, so, a truly excellent uh, issue of the Scientific American magazine. I keep getting this February of this year, and you'll see Origins of Space and Time. This is a great article. I've only read it twice, and so it's going to take another time or two. But one of the beautiful things that comes out of this is that physicists, especially string theorists, are working with the idea that space, time and space, are not fundamental. They are emergent. So this picture you see here on the top, this weird wiggly thing, is their attempt to depict the notion that quantum entanglement may be more fundamental than space and time. And space and time, as we experience it, has something to do with the nature of our consciousness, the way our consciousness is instantiated in reality, and the way in which quantum entanglement at the next level down, whatever that is playing out. And regions that seem close in space to each other might actually simply be more entangled from a quantum mechanical point of view than ones that seem far apart. Now, there's a lot of problems in that statement. I can immediately pick it apart for you and explain why you shouldn't believe it. But that's a quick approximate presentation of that idea. There's three different lines of logic from this particular article that are being sketched out. One has its origins in string theory and arguments of Leonard Susskind and other of the leading string theorists. There's another theoretical paradigm called loop quantum gravity, and yet a third one called causal set theory. All three of them, in different ways, are pointing to the idea that space and time are somehow emergent approximations of processes of entanglement or interaction happening at a more fundamental level of reality than what we perceive and what we've been able to measure up until now. So that's like, wow, super interesting. Then, let's see here. Oh, I know what. So, a book I've been reading for about 4 years. It turns out to be quite relevant to this topic. I've been reading this for 4 years and I'm only on chapter 5. But it's good timing because here's the title of chapter 5. Emergent Spacetime. Now, I'm only 2 pages in, but I'll keep going. You can tell I'm slow, but I'm persistent. I'm the tortoise kind of person. And I want to close on a final thought here. So something I mentioned a little while ago was the fact that quantum mechanics, which is one of these two parallel big branches of mind-boggling stuff that came at us in the 20th century, quantum mechanics was forced on us by observations. Nobody wanted quantum mechanics when it first showed up. It was fought tooth and nail too, just like everything new is. Well, people had to accept it because unless they accepted it, they were never ever going to explain what instruments in the lab were showing to be the facts. Okay, so this is a talk to the Theosophical Lodge. I can be a little adventurous here. Let me talk about how we might broaden that concept out and bring it home to roost and use it as a guidepost for how we look at these things going forward. A book I believe I have mentioned to you and shown you before is this absolutely beautiful book by Russell Targ, who is just extremely far out guy. So this is a book, I think it was published in 2004, and it has a lot to say about Tibetan Buddhism in it, and even more to say about his experiences as one of the people who established remote viewing as a scientific protocol, as a way to sit people down and teach them how to perform inarguable acts of psychic functioning, acts that we might call clairvoyance. It's an easier word for the typical scientist to say is to use remote viewing, and it is now taken on like wildfire because it turns out to be a reproducible thing. It's a protocol that, some people are better at it than others, but most people can be taught to do remote viewing to an extent that it can be useful to them. And it's useful to law enforcement, it's useful to military agencies, it's a useful thing. Well, one of the very interesting early observations, this popped within the first 10 years of the paradigm, and when they were using remote viewing, and they were using the methodology where there would be a receiver sitting in a lab at SRI with a sketch pad waiting to obtain information from somebody who was out somewhere in the wilds of Palo Alto or Menlo Park looking at something at a certain location, and then they would have a moment where the receiver would sit and sketch and free associate, sometimes speaking words and sometimes drawing, sometimes all of the above, and testing for, is there a reproducible, no kidding, information bleed coming from the viewer to the receiver. It was established beyond any doubt of a person who wants to look into it seriously that this works. Furthermore, what was established is that the information sometimes would transcend time. So it was not simply transcending space, it was transcending time. Because on more than one occasion, the information that came through to the receiver and pictures they drew had as much to do with the way that location looked at some point in the past as with what it did right then that the viewer was looking at it. There's one particularly stark and famous case that I don't have it flagged in the book, but I'll show it to you sometime, where the viewer perceived an old style farm windmill and a water pump tower kind of an affair on the piece of ground that was the target site, that was no longer there in the present moment, but had been there not that far in the distant past. That dislocation in time cropped up enough times that it became a given. This is part of how remote viewing works. Okay. I would propose, as someone who is interested in studying physics and consciousness and the nature of space-time and our relationship to it, that is one of those facts that needs to be folded into the matrix of things we consider as we construct a theory of space and time and who and what we are in relationship to it. And the good news is there's a lot of people who are doing that. I'm not the only person who thinks that. So stay tuned. I think we might be on the cusp of some pretty interesting, pretty large revelations. So you'll be hearing things from me in the future about emergent space-time, probably a lecture or two devoted simply to what the word emergence means. What are examples of emergence? That's kind of a separate topic that deserves some time and attention all on its own. And so that's it for now. This is Jeff Curtis in the Sierra Foothills, wishing you guys all the best, and thank you for coming by. And I will see you next time. Bye.